Yes. So, in the previous classes, for last two classes, we were discussing some problems on pericyclic reactions. So, we have taken some problems and we have tried to solve it. So, it is a cascade of pericyclic reactions, like it involves, like we have seen that in electrocyclic ring opening happens, in some cases electrocyclic ring closures, then we have seen some sigmatropic reactions, cycloaddition reactions. So, putting together we have solved some good number of problems. So, this class also we will try to concentrate on some more problems, and after once we finish that, then from this class one more class we have. So, in that we will try to discuss about others type of pericyclic reactions like heliotropic reactions and so on. Okay. So, in this class again we will try to discuss some more problems on pericyclic reactions. And, if you remember, in the first problem of pericyclic reaction, we were trying to see the synthesis of antiandric acid, right. So, but we did not took it, I just showed you some important reactions involved in this synthesis. So, what we will do this antiandric acids are not only one, they are from A to D. So, what we will do in this problem, we will try to see all the synthesis of these acids and what type of pericyclic reactions are involved in that. Okay. So, first we will try to synthesize, we will take cyclo octatriene, right. So, we will take the system. Okay. We have a phenyl here, fine. So, then we will have here, you can have a carboxylic acid or you can have CO2R. And you know how I have made this compound. If you refer the first problem, you can have an alkyne type of system where you use your Lindar catalyst and reduce to get you this one. Now, what happens to this? See, if I do my sort of electrocyclic reaction, for example, I take this, okay, and I heat it. So, what system is this? We can call this as a EE, right? Yes. So, what system it is? It's an, if you involve this one, this is a 8 electron system, yes. So, again it will follow your 4n rule. So, what, so it is a 8 pi electron system, right. So, it follows a 4n rule system. So, what is that on heating, whether it is dis or con? Yes, it is con rotatory. So, you get a con rotatory. So, what happens? And you know about the con rotation mode, right. Either it should be the clockwise, you can think about clockwise, both should be same direction because it is a con rotatory, okay. You can think of clockwise. So, then you get a product, fine. So, one should be outside and one should be in. So, both will be in different plane. So, then you get a phenyl and you get a double bond and you get a phenyl, okay. So, you get a system like this. So, this side it should be other way around. So, you get CO2R, fine, okay, CO2. Now, what we will do? We will take the same system, fine. Now, as I said earlier cases, so if I again heat this, what it is? Now, it is a 6 pi electron system involved. So, it is a 4n plus 2. So, what is that corner? Yes, it is a disrotatory. That is good. Have a disrotatory. Once you have a disrotatory, then you know how to cyclize this one. So, a cyclize system like this. If you want, you can put a boundary. So, you will get like that. So, if I draw it, so you will have this. So, my hydrogen will be out, right, and then I have my, this is my the part. I have a phenyl here, okay. I have a phenyl here now, it's clear, and then you have an hydrogen and you have a Rs to C. So, you have your acetate. So, you get this product, fine. This you can call this as an end andric acid, okay. Andric acid, it is D, okay. It is called end andric acid D. Clear up to this. So, first I have taken a system, okay. This is an 8 pi electron system. So, follows a 4N rule, heating, undergoes a Kohn rotation to give me this product. Now, this product again on heating undergoes a 6 pi electron system, which is your 4N plus 2 rule. So, it undergoes a disrotatory to give me this product, which is a ND andric acid. Clear? Any doubt with this? Okay. Now, if you take this same compound, I can write the same compound in this fashion. There was same similar compound, I can write like this. Slightly like same compound I am writing, okay. Not like this is E, fine. Okay. What I will do, I will write here so that it is looks big. Okay. See, previously it is 8 system 1, 2, 3, 4, 5, 6, 7, 8. You have this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, that is good. So, this is nothing but is the ZZ form of this. So, EE and this is the Z and Z of this. This is Z form and this is just I am taking this in 2 different forms. You can write this, it can exist in E as well as you can write it in Z. Any doubt? Okay. Now, I can say the same thing for you. Okay. If I heat this, so what you can think about? Yes, it is a similar system. See, it's again it's a 8 pi electron system, nice. So, it is a 4N rule you can apply and you can say what rotator it is? Yes, good. It is a, again you can write a Kohn rotatory for this. So, the how the product will be in this case, it will be similar. Clear, but now it will be just the opposite of that. So, you have phenyl here, okay. Just see the stereochemistry, then you will know you have just got the opposite one, CO2 R. Just check this part, they are just opposite. So, here I have taken the EE, so it can exist like this as ZZ. Okay. Now, again I say that I am going to take this part, heat it. Okay. So, what happens? It is a, again it is 6 pi electron system. So, again I can use the same rule 4n plus 2 and this rotatory, which is similar for the previous case. Okay. Clear? If you want, you can. You see now the product, how it looks like. So, you have a nitrogen here, you have a nitrogen here. That part is clear, that is not a big. So, now what will happen, because you will have a CO2R, right. So, it should change it because it is a dis. So, you will have this CO2R and you will have your hydrogen here and you have the other phase of it. Okay. Then you have a double bond, then you have a double bond, okay. You will have a phenyl. Clear? See how this two product, now this is called as N-D-andric acid E. Okay. So, what is this two? How they are related? How they look for you? See, they can be, I can just do like this. Is it possible? What they are? Yes, they are nothing but diastereomers. Stereoisomers. Okay. So, now you have this 2 1. Now, tell me, okay, I will just write for you one more time the product. I will write N-andric acid as well as N-andric acid E. Okay. Just for your sake. Write a separate for this, so that hydrogen here, CO2R, I have an hydrogen, phenyl here. In this case, this is N-andric acid T. Same way I can write for E, because they are nothing but, just we said it is diastereomers. So, we have a hydrogen here, okay. But in this case I will have my CO2R hydrogen, on the other side I will have my phenyl. Okay, I will have this compound. So, if you see, both of these are diastereomers, as we said. Now, I ask you a question. Which of these two, among these two, you can expect which will do Diels-Alder reaction? I have this two. Consider one as a it's an intramolecular Diels-Alder reaction. Whether this will go intramolecular Diels-Alder reaction or this will undergo intramolecular Diels-Alder reaction. Which will undergo intramolecular Diels-Alder reaction? D or E, which will undergo intramolecular Diels-Alder reaction. Yeah. So, D will not, because your diene and your dienophile are in the opposite. Okay. In this case, if you see this part, if I write it if I will write it for you, just look this molecule. to R this part can I like this. Now what will happen? You just see this. So I can do this, right? This is what? Yeah? Yes, 4 plus 2. So you have a 4 plus 2 cycle addition. So you can nicely it can do a Diels-Alder reaction. In this case, you cannot do it because they are in the opposite phase. So here we can say that your that Diels-Alder reaction, okay, it's not going because you are dyne and dynophile or on opposite side. Clear? So, but here it can undergo a nice Diels-Alder reaction. So, you can write a good Diels-Alder for this. So, you have to just connect this Diels-Alder reaction. Just write the structure. So, it should be fine. So, you will have your phenyl here, you have a double bond. First finish the skeleton of the molecule. So, you have finish the skeleton first, okay. Fine. Now you fix your hydrogens, the stereochemistry. So, you get this product, just it is a Diels-Alder reaction. Any doubt? So, you we have taken a system like this, we did heating, gets you a cyclized one, then you again heat, then it undergoes a 4n plus 2 disorder to give you an end-andric acid D. Same one, this is EE form, I am taking the ZZ and you get an end-andric acid E, which are the diastereomers of each, and then I am taking your andric acid D and say that whether it will undergo Diels-Alder reaction. You said that it won't because your dyne and dynophile are on opposite side, but in the case of andric acid E, it undergoes nicely to give you this product. What is this? Yeah, this is your andric acid A. So, you know now you have A, you have E and you know D, clear. So, that is how it works, okay. So, you have it has a both ring closures, one follows a 4n, another follows a 4n plus 2 followed by a nice intramolecular Diels-Alder reaction to give you the product. Any doubt with this? Because using the same idea we will do for end-andric acid, we will synthesize B and C. We will see how the synthesis of B and C, just it is much more similar like this. So, if you have any doubt, please let me know. Okay, then it is fine. Then we will go for synthesis of B and C. It is a similar system, just similar like this. So, you have again I am taking the system, but only the variation I am looking for is there will be a okay, you have a phenyl which is the EE form of it. Just this part your acid is little bit different, okay. I am taking this type of molecule in this case. Okay, this is the E of it. I am taking fine. Any doubt with this? Okay, that is good. Now, as I in the earlier case, as I mentioned in the earlier case, if I heat this, what you are going to expect? Again, it is a similar, it is a 8 pi electron system, very good. So, 8 pi electron system, 4n rule, and you are saying it is a con-rotatory. So, nothing but do a cyclization. Oh, sorry, you do not have a double bond there, you have a double bond here, not there. And you have a phenyl, and you have a double bond here, and you have a phenyl. You get this one, and this side you will have your carboxylic acid. You get this product nicely. Now, again I am saying what we can do. You guys know that, yeah. Again, if I heat it, so it is a 6 pi electron system. So, I can do 4n plus 2 and this rotatory. So, nothing but I get a system like this. So, if you draw the structure, this side you will have your carboxylic one, right, double bond, and you have your carboxylic acid. So, you have your hydrogen, and this side you will have your phenyl, one have a double bond, then you have a double bond, then you have a phenyl. Clear? So, you get this molecule. Any doubt with this? No. Same way I can say that for this E, okay, can I write the ZZ form? Yes, because I have shown you in the earlier class, you can easily draw the ZZ for this guy. So, just you have to okay, you get this one. So, you have a double bond, okay, you get this one. Now, so you have a phenyl here, fine, okay. Then we have a, so you have this one. So, the next part of yours will be double bond with a COOH, right, okay. So, you have this part, this is your ZZ, okay, this is your E and this is your ZZ form. Now, again I say that use the same condition as earlier, heating 8 pi electron system, you can apply same thing 4n and con-rotatory. So, it should be the similar mechanism. I should get a ring closure here to give me okay, it should be just the reverse and the okay. phenyl. So you get this one. Okay. Now again you can heat this. It can undergo a nice 6 pi electron system. Same way 4n plus 2 you can up, and you can do a this. So you write the structure for this. We have a nitrogen here, but this time it should be the other way around. So you have your phenyl here, okay, and you have your carboxylic acid. Here you have carboxylic acid. Fine. So this we call as, this is your ND andric acid F, okay, and this is nothing but ND andric acid, that's F, and this is your G. Okay. Now you have these two molecules. Now tell me whether they will undergo Diels-Alder reaction, andric acid F and G. Yes, both will undergo nice Diels-Alder reaction. We will just see, we will write the structure again ND F and G and see how it undergoes Diels-Alder reaction. Okay. So how was the structure? So this is this case you have carboxylic acid outside, you have nitrogen here, you have phenyl here, phenyl here. So if, and I have nitrogen here, hydrogen here. So I can, whether this will undergo a Diels-Alder reaction? Yes, it can undergo a nice Diels-Alder reaction. So your, this can be your 4n system, right? This 2 can be a 4n system, and this will be your, so this is your 4 and this is your 2. So 4 plus 2 cycloaddition. You can easily think about your Diels-Alder reaction for this, giving you this product. So write the product like similar to, it will be like ND andric acid, but the stereochemistry will be a little bit different. So you have phenyl, you have your hydrogen, okay, hydrogen here, hydrogen, you have your carboxylic acid outside, and then you have this one, hydrogen, you have double bond. Yes, clear? So this is ND andric acid B. Fine. So you have taken ND andric F, right, and then you did the Diels-Alder on this, you got an ND andric acid B. Same way now we have to do for G, the other diastereomer, right? We can do for G also. So first this is F. Okay. Now we will do for G. G will be quite interesting. So I have a double. I have an hydrogen here. Okay. carboxylic acid. Fine, this side is your phenyl. Fine, your nitrogen, your nitrogen. Now tell me how dienes are there. See, in this case, in this case you have your diene, like you have your diene here, then alkene here, right. So, two electrons involved in this ring and 4 electrons was involved in this ring, right, 4 plus 2. Here how it should be in this case? But first tell me whether it will undergo Gill-Sadler. Yes, it will undergo Gill-Sadler reaction. So, it will undergo Gill-Sadler reaction, but how different it will be? Yes, in this case it will be just the reverse of it. This will be your diene system, this will be your alkene system. So, your 4 electrons comes from here and your 2 electron comes from here, clear. So, now if you do the Gill-Sadler, now draw the structure, just see how it can add up, draw the structure. Best way to draw it is like this. When you have alkene here, you have a carboxylic acid, then I can have phenyl, then I have my hydrogen, 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 this. Okay, you can draw the structure like this if you want to do the Gill-Sadler reaction of this one. Clear? So this is called as ND, andric acid. C. Again, this you can always reverse this part, right? Any doubt? So, what we have seen is that we have now we took like same type of similar systems, we had the EE form, then just we took the ZZ of that, okay, and then we did a similar pericyclic cascade reaction. First it was a 4n con rotatory, followed by 4n plus 2 disrotatory, then your intramolecular Gill-Sadler reaction. Okay. So, you got ND andric acid F, ND andric acid G, ND andric acid D and E. Only your D was not able to do the Gill-Sadler reactions, other 3 finally did intramolecular Gill-Sadler reaction to give you the product A, B and C. Clear? So, this is very interesting part, nice to study about, because you know much about this pericyclic reaction once you solve the problems. Any doubt in the synthesis of andriac acid A to D? Any doubt? Okay, that is good. Now, we will take one more good example and see how we can solve that. Okay, that is a nice example. A system of aromatized Okay. So, I have a starting material like this. So, I am saying that again a starting material. Okay. I say that you can take this starting material and slightly heat it and eat it. Okay, not slightly, heat it. So, what you can think of? What reaction comes to your mind? Is it is a ring opening or anything? Which reaction comes to you guys' mind? Because you can see the system. Yes, that is good. So, it is nothing but it is a 3,3 sigmatropic. That. So, see, after doing problems now you guys are good. So, it undergoes a 3,3 sigmatropic shift. Just 1, 2, 3, right? 1, 2, 3. I can do it. So, think of this part, and think of this one, right? So, that gives me a product. A product like double bond S. CH2H and you have here aromatic. Now, what happens? Yes, that is good. Regains its sort of aromatic. This hydrogen gets it back. Okay. So, you get this product. Oh, SH, you get this one. Okay. This system, now I take this system, I say that I will heat again this molecule. Tell me what you can expect now. Now, you should be like little bit like once you have seen several problems, now you should be little bit faster what you are going to do, because nothing going to happen here. Okay. So, no cycle addition or anything you can think about. So, which will be, because now you guys are fast. Yes, that is good. So, it is nothing but it is a 1,5 hydrogen shift. You can expect 1,5 hydrogen shift like this. So, 1, 2, 3, 4, 5. So, I can push this one, push it up. Okay, sorry, I can push this down, right? I can push it up. Your hydrogen goes here. Fine. So, this double bond, and hydrogen goes here to give you double bond. Yes. Okay, once you shifted, double bond is not there. So, we have a something like this. Oh, yes. When I have a shift of double bond here, so I have a double bond, then okay, yes, SH. So, after this, once you get this product, what you can think about? Once you get this one, now I say that this molecule I am going to just heat it again. See, first you did a proper sort of cope, thiocope you can call it, or it is a 3,3 sigmatropic shift. You got this nice product. Then what you did? Then it regains aromaticity, so you changed it to this form, which happens very fast, and then on heating it undergoes a 1,5 hydrogen shift. After this, Now I am saying I am going to heat it. What you can think about? What system you are going to do? Yeah, because you have a you can easily do a ring closure, right? Yes or no? That's all, you are done. So heating. So what is this? It's a 4n plus 2 system. So I can think about a this type of closure to give me a fine. So see, you did 3 comma 3, 1 comma 5 hydrogen shift, 4n plus 2 ring closure to give you the product. See, you have created, you have generated a new ring here. Okay. So we will do one more nice another reaction. One more problem on this. Once you keep on doing problems in pericyclic reaction, you get like really you will get, see this most of the time you involve electrocyclic ring closure, ring opening, either it is a hydrogen shift or some cases you have methyl shift or intramolecular Diels-Alder reaction, some cycloelimination, ring opening reaction. That's all. Most of the time your cope 3,3 is very fissile. Okay, that's what I said. Just look in your pi system of a given substrate. Taking a system like this. Okay, 6 member. Okay, so 6 member. Right. Now I am saying that I am taking this starting material and I am heating it. Now tell me what comes to your mind immediately. What you are going to expect from this once I heat this. Anything comes to your mind immediately? Yes, good. It's nothing but it's a 4n plus 2 electrocyclic ring opening. That's all. So I have to just move this apart. This opening of your 5 member ring to give you so you get this product. Now anything you can think about after this, any other pericyclic reaction comes to your mind. Once I take this molecule and eat it, can you think about any other pericyclic reactions? Little bit tricky, but if you, it's easy, it's not that hard. You have studied that. Just can you think about it? Okay, I will tell. It's nothing but you can have your nice methyl shift. See, all the time you are looking for your hydrogen shifts, right? This case it's a methyl shift. This example involves a methyl shift. It's a 1,2 sigma tropic methyl shift. Nice to see examples like this, because you should not like always you think about only 1,5 hydrogen shift, 1, photolysis you get 1,7 hydrogen shift. See, that comes very easy, nice to your mind always. But even metal shifts you should observe, like there are many examples where you can see metal shifts. So in this case you can see I have a nice metal shift. So you get this product now. Now if I say this one, I say that I am taking this product, okay, I'm slowly warming it up or heat under the heating condition. What happens to this? Anything you can expect from here? Yeah, sort of ring opening, okay, sort of ring opening. See, it's nothing but this, it's a sort of ring opening system which you have to normally understand. Okay, can get it. It's called a cyclo-elimination type of ring opening. This one, okay, so they call a cyclo-elimination. It also it's nothing but it's a 4n plus 2 system, right? So just the ring opens to give you N3CH, that's your HCN, plus get O double bond C plus double bond NH, and you get the other side of the product. So you get 3 products out of it. So it's just a cyclo-elimination, just opening up of this ring formamide and then the other part of the unit. So you get the 3 product of this. But this is just leave it. So first on heating you get an electrocyclic ring opening, then you get a 1,2 sigma tropic shift, then you have a 4n plus cyclo-elimination. Fine. Any doubt with this? Okay. Fine. Now what we will do, this will be our last practice problem, okay. So we'll do the last practice problem and then we can move to our heliotropic type of reactions. That's all. This involves maximum problems once you know this. So we'll do the last one. Taking a system like this, hydrogen, R, have a propyl here, okay. I am going to treat this with this molecule, sort of a cyclohexanone system with a methyl here. So this I am going to do photolysis. I am going to photolyze this one. So what you are going to expect? Oh, sorry, I have not. You have your system here with a pi 2s plus 5 4. You can have a double bond with your system here. Clear? So now you do. Now you tell me what you are going to expect from this molecule. Yeah, it's nothing but a cycloaddition. So these things are very simple to understand, right? So you undergo a cycloaddition reaction. So I can draw the molecule. Okay, this part is not going to change much. are here, have my propyl here with my hydrogen in this case outside, and I have my hydrogen here, hydrogen. Then you have a methyl and you have hydrogen. See, you get this nice cycloaddition reaction. Now, if I just slightly warm this, you can think about a opening, heat this, you can think about a pi 2 S plus pi 2 A cyclo elimination. And get a nice cyclo elimination to give me hydrogen. R here, propyl here. Then you have your hydrogen and you have your methyl. Okay, so you get this system like this one. Now tell me what you can expect from here. That yes, very good. So you can have a 1 2 3 sigmatropic. So 1 2 3 and 1 2 3. Can have a sigmatropic 3 3 sigmatropic shape. Give you propyl so you get your product, you get your 1 2 3. So 3 3 you get your comp. So what happens, this again undergoes a bond rotation and then again it undergoes a 3 3 sigmatropic shift. Okay, this undergoes a slight bond rotation, then followed by a 3 3 sigmatropic to give the final product. Fine. Any doubt with this? Okay. So, so these are like several problems which you can work on pericyclic reactions. Okay, there are many other problems which you can get. Just see your pi system, then slowly understand what major reaction it can happen, whether it is a cycloaddition reaction or it is an electrocyclic reaction or sigmatropic. See the condition whether it is heating or what. Then you decide among electrocyclic whether it is a ring opening or ring closure. Then you come down and say whether it is a con or dis. Same way cycloaddition, you think whether it is a pi 4s plus pi 2s or what it is. In same way like 3 3, you see the condition whether it is heating. Same way you can think about hydrogen shift 1 5 1 7. Same way you can think about your methyl shift. So put all these things together and then you can solve problems. There are many problems like this which you keep on work out and you will get it. Okay. So this about all the practice problems of pericyclic reaction. From next class we will, and the next 2 class we will try to focus on some important other part of reactions like stereotropic reactions, and we have coarctate reactions, and then we will see some applications of photochemistry, like new applications like photolithography. I am not going to explain you in detail, but I will just take you some overview on them, like what is photolithography, what is new photoremoval protein groups, how they are used to release cage molecules, like that. Okay. So we will just study some, next class study some pericyclic reaction, finish it off, and finally we end up by seeing some application of photochemistry. Okay. So that is the end of this class. Thank you.